You floated the possibility that 3i Atlas is alien technology in order to distract us from the Epstein files.
3i Atlas's gravity is dragging Mars toward Earth. Collision confirmed. A bright, cold pinprick in the dark, a silvery halo that refuses to fade. Telescopes in backyards and mountaintop domes tracking its steady, strange approach. What if that tiny point of light was not just passing through, but changing the paths of worlds? The mainstream view first. An interstellar visitor, a comet on a long, hyperbolic arc. It swept through our neighborhood, wore a tail of ice and dust, and moved on. We had seen visitors before. Oumuamua was odd. Borisov looked like a comet. Most scientists expected curiosity, not catastrophe. Observation would yield a paper, then life would go on. But the numbers did not fit that easy story. Between May 15 and September 23, 2025, observatories around the world locked on and did something rare. They pooled resources. They measured everything. 4,022 measurements, 227 observatories. Night after night, the picture sharpened. What emerged was not a fading speck. It was a growing, glowing thing. When first detected in May, the object labeled 3i Atlas was estimated at 10 billion tons. Massive, yes. Manageable, perhaps. By September 23, it had tripled, 33 billion tons. Its nucleus, by simple estimates, had swollen beyond 5 kilometers. For scale, remember this, Oumuamua was mere hundreds of meters. Borisov around a kilometer. 3i Atlas dwarfs them. On paper, these are numbers, a scientist says in the lab, voice low. In planetary terms, they are a different order of danger. The path it took was not a slow, gentle curve. It is hyperbolic, unbound to the sun. It screams through space at roughly 60 kilometers per second. In common language, faster than most things we send from Earth and not coming back. That should make it a visitor with no lasting effect. Instead, the visitor appears to be grabbing at the stage itself. Harvard astrophysicist A. Loeb, working with Richard Cloudy and Peter Veris, coordinated the global campaign. Their models suggested something unnerving. Not only was the object growing, its field, both gravitational and magnetic in the models, was interacting with nearby bodies. In short, it was tugging. The data show a tiny but measurable drift in Mars's orbit. Call it a whisper on the cosmic scale, about 0.0202 astronomical units per year. That's roughly 3,000 kilometers of drift from predictions. Tiny for humans, huge for planets. Orbits are balances. A small shove applied repeatedly changes everything. Rovers on Mars report strange things. Magnetic fluctuations stronger than expected. Dust storms forming weeks too early. Seismometers detecting subtle vibrations that managers didn't expect. On a world that has held the same rhythm for billions of years, small changes are meaningful. Mainstream explanations arrive first because science favors the simplest model that fits the facts. Perhaps observers overestimated size. Perhaps a modeling parameter was off. Perhaps a localized jet of gas made the light curve look odd. Comets do strange things. Dust and jets can create illusions. Most researchers want to test that first. Most signs still point to a cometary body pushed to extremes by physics, a team member says. We must evaluate jets, outgassing patterns, collisional fragments. We start there. But then anomalies pile up. The object is getting brighter as it approaches. Comets usually lose mass. They shed ice and dust under sunlight. This one seems to self-amplify. It seems to gather. Instead of thinning, it thickens. Instead of disintegrating, it grows. A second anomaly, the magnetic readings. Models by Loeb suggest a magnetic sheath perhaps 150 times stronger than Mars's global field. Imagine Mars' faint planetary magnetism, then multiply it by a factor measured in the low hundreds. The field extends hundreds of thousands of kilometers. It interacts with the solar wind like a small magnetosphere of its own. Magnetic coupling is a big deal. Fields twist, connect, and torque. They can channel charged particles, change atmospheric escape rates, and in extreme cases, exert forces that amplify gravitational interactions. Think of the object not as a rock, but as a magnetized beetle crawling through a pond, tugging at currents and filaments around it. And then there is the mass. How does something go from 10 to 33 billion tons in months? Some suggest it is sweeping up material. But the density required to capture that much mass in the vacuum between planets is astronomically high. Another idea, internal collapse. Voids inside the body could compress, changing density, but that alters density, not total mass. A radical hypothesis circles the labs, self-assembly. The object might be capturing and integrating material into a growing core, a seed crystal capturing more and more atoms. If a technical artifact, a construct, is designed to grow, it would behave like this. It would not be a cometary rind. It would be a machine. Self-assembling is the least comfortable but most consistent with growth and field, Loewe told colleagues. If we accept that, the implications are profound. Yet the majority of astronomers remain cautious. Extraordinary claims need extraordinary evidence, so they return to measurements. The Mars Reconnaissance Orbiter was tasked to help. On October 3, 2025, MRO was scheduled to take images at about 30 kilometers per pixel as 3i Atlas brushed past Mars. That resolution cannot see small instruments. It cannot tell us whether an object contains engineered geometry, but it can refine a nucleus size estimate and set constraints on albedo and mass. If MRO confirms a nucleus larger than 5 kilometers and mass above 33 billion tons, the standard models of interstellar debris will fail to explain this. If the field continues to straighten and hold, we must face a different class of object. What forces could make something tiny yet so influential? Gravity accumulates. Even a small force applied consistently over time can push a planet thousands of kilometers off its path. Imagine nudging a clock hand by a fraction of a degree every hour. Over a year, the dial changes, but magnetic coupling can amplify that push. A magnetosphere interacting with Mars' ionosphere can induce drag, it can torque field lines, it can couple angular momentum. Combined, gravitational tug and magnetic torque can change orbits in ways that are disproportionate to mass alone. If the coupling hypothesis is right, Mars is the first victim because geometry favored a close brush. The object's orbit bites the ecliptic within a few degrees and passes near Mars's orbital plane. When the two paths come close, the field lines braid. The result is not merely a pull, but a twist. The stakes are hard to overstate. In the best-case scenario, 3i Atlas proves a weird comet. It stabilizes. Mars gains a wobble. Satellites retune orbits. Rovers adapt. Scientists write papers. Social media forgets. In the middle scenario, Mars's orbit becomes more eccentric. Its moons, Phobos and Deimos, could be nudged into unstable paths. One or both could break up, forming temporary rings or raining debris. And the worst case, a shift that, over successive orbits and resonant interactions, sends Mars onto a path that could intersect Earth after many rotations. Or, more likely in some models, the disturbance could destabilize the asteroid belt. Objects could be flung inward, producing waves of meteor storms and a slow-motion bombardment of inner worlds. Planetary billiards would replace clockwork. Small changes compound, Loeb said. Orbit is history. A tiny push today can be a collision in a century. We must be clear. These are scenarios, not prophecies. The models are complex. They depend on mass, field strength, orientation, and timing. They depend on things we still do not know. Yet signs on Mars are already visible. Dust storms earlier than predicted, magnetic glitches in the ionosphere, subtle quakes that don't match expected tectonic patterns. These are early fingerprints. They do not prove doom, but they demand attention. People predictably reacted quickly. Social feeds filled with panic and poetry alike. Backyard telescopes posted images of a greenish coma and a long silvery anti-tail. Discussion forums debated whether this was a planet killer, an alien probe, or a natural marvel. NASA and SA quietly ran models. Planetary defense units discussed contingencies. The tools for deflecting a comet, kinetic impactors or nuclear nudges, do not work for gravitational perturbations of a planet. Gravity cannot be blocked by explosives. It can only be measured. Private groups, less quietly, began funding alternative habitats and survival projects. Bunker schematics circulated. Engineers and ethicists argued about the prudence of panic. The public heard fragments. The truth is messier. Scientists are modeling outcomes, probabilities, and uncertainties. In the lab, the discussion turned to observation strategy. How do we measure a magnetic field at hundreds of thousands of kilometers from a small body? We use proxy effects. We watch charged particle flows. We measure bow shocks. We look for deflection of solar wind and perturbations to plasma tails. Spectroscopy offered clues. Observatories, from Chile's Atlas system to space telescopes, detected water ice, carbonaceous minerals, and silicates. Those remain consistent with cometary chemistry, yet composition alone does not explain the growth or the magnetic strength. If the body harbors ultra-dense materials or exotic coupling between magnetism and mass, the laws we trust might be incomplete. Physicists speak carefully here. New physics is a difficult, rare thing, but when existing models are stretched across disparities, new theories are considered. Some researchers advocated a more conservative approach. Assume natural until proven otherwise, one consensus read. Test jets, map dust production, watch rotational states. The simplest model has a strong track record. It's how science conserves itself against wishful thinking. But other teams designed contingency experiments. They retasked Mars orbiters, asked Juno to shift observation plans for its March 2026 flyby near Jupiter, and lined up the Vera C. Rubin Observatory and other survey telescopes. Every dataset sets a new constraint. Every observation rules out some possibilities and privileges others. The physics of cumulative change is non-intuitive. If Mars's orbital period changes by a tiny fraction of a percent, resonances change. An asteroid in the belt that had a harmless dance could find itself nudged into an inner path. The inner system could see an uptick in small impacts. Over decades, the cumulative effect could change climate, impact rates, and even mean solar insolation in subtle ways. In laboratories and control rooms, human stories unfolded. Graduate students pulled all-nighters to reduce spectra. Engineers retooled tracking algorithms. Amateur observers in backyards emailed discovery notes that helped point larger telescopes. The scramble was a human chorus, underscoring how fragile and flexible our modern observation network can be. So what are the leading hypotheses today? First, a highly active, unusual comet. Jets and fragmenting matter could create apparent mass changes and odd light curves. Second, a self-assembling natural process where material accretes at unexpectedly high rates. Third, a body with ultra-dense material or an unknown coupling of gravity and magnetism altering its effective influence. Fourth, a technological construct, a probe or machine that grows by design. Each has consequences. The comet hypothesis is manageable. The ultra-dense or exotic coupling hypothesis forces a rewrite of planetary science. The machine hypothesis forces questions about intent, origin, and ethics. We must also account for observation limits. Geometry matters. Between late autumn and the sun's glare, Earth-based telescopes lose clear sight. During certain windows, only space-based instruments can observe. That is why the October 3rd MRO pass and the March 2026 Juno opportunity are not mere data points. They are golden windows. If you imagine a clock, there are moments when the face is visible and others when it is not. The next months are our visible moments. We must use them. Amid the models, practical steps began. Space agencies cataloged mission-critical satellites. Engineers modeled how to shift Martian orbiters if needed. Communication plans were rehearsed. But there is no shield for gravity. The only defense is information. And yet, human resilience shows a quieter story. Scientists, often caricatured as ivory tower figures, became storytellers and communicators. They explained uncertainties in plain language. They emphasized the range of outcomes. They helped gardeners, school teachers, and city planners understand probability, not panic. As for the sensational claim that Mars is being dragged toward Earth and a collision is confirmed, the evidence does not yet justify that headline. The scenario remains possible in certain chains of events, but it is not a foregone conclusion. Science requires patience. It requires data. It requires us to say, we do not know, but here is what we do know. So where do we go from here? Watch, measure, model. The nights ahead will be full. Observatories will keep stamping patterns on data sheets. The MRO images on October 3rd will refine nucleus size and albedo. Juno's flyby in March 2026 will probe interactions near Jupiter and set new mass constraints. Ground-based surveys will watch the coma and tail and search for jets or fragmentation. Meanwhile, the debate will sharpen. Some researchers will argue the body is a rogue planet fragment, a remnant of a disrupted world. Others will push the self-assembly idea, studying how accretion might operate in a low-density environment. A vocal few will speculate about engineering. Each idea invites experiments. In the end, our response must match the scale of uncertainty with humility. We are good at taking measurements. We are less good at predicting rare events with incomplete data. But history favors those who observe patiently. Right now, 3i Atlas hangs in the sky like a warning and a wonder. It is still distant enough to seem abstract, yet already powerful enough to tug at a planet. The story is not over. It is only beginning. What do you think it is? A massive comet pushed to extremes by physics? A self-assembling body that defies classification? Or something else entirely? Drop your theories below. Subscribe for the next update because the next few months could rewrite our picture of the solar system. And one last question to leave you with. If a single visitor can change a planet's clock, what does that say about how small forces shape the fate of worlds?